From a previous video, we found that we had this variable u equal to this, and ultimately this came down to, we can find r is equal to b squared over a1 plus the eccentricity times the cosine of theta. As long as, if we can show that this is true and this is true, then we can, from the connecting with the previous video, show that planets travel in an ellipse around the sun. There's one small correction that we'll do in a different video. It doesn't affect the derivations we do here, just affects the symbols that we used. So we're going to start out with remembering that this is the angular momentum we had earlier. That's equal to m mass of the planet or whatever we're dealing with, r squared omega. If you recall that v is equal to omega r, so this becomes mvr. So if we think about the ellipse traveling, or a planet traveling around, where this is the sun and this was that planet X moving around, it's going to be moving closer at this point than at that point. Kepler's second law, since it sweeps out equal area in equal times, it has to travel faster if the base is smaller. At the closest point, known as the periapsis, the angular momentum, well, that's equal to a constant, but that would be mass of x times the speed at this point right here, which I'll label as p, and then the radius p. So the speed at p is equal to that constant angular momentum, mx rp. If we look at the farther spot away, the apoapsis, and don't know if I'm pronouncing it right, but that's what I'm going for. We can also, similar reasoning, that the speed at the farthest point is equal to L over mass of x times whatever that distance is. So sort of keep that in mind. We will come back to it. Now, energy is conserved in this, and so we haven't necessarily dealt with energy yet, but E is equal to K plus U. This is mechanical energy. We're not talking about any mass to energy conversion here, so we got kinetic and potential energy. Kinetic energy is 1/2 mv squared, and potential energy is the one associated with the gravitational force, is negative g, mass of the central object, mass of planet X, so that's for X, over r. And so if we look at, since energy is conserved, this value at the nearest point should be equal to the energy at the farthest point. And so we have 1/2 mxva squared minus g mass of sun, mass of x at Ra equals 1/2 mxvp squared minus g mass of sun, mass of x at Rp squared. So this is energy conservation, which potentially is a chapter after you're looking at this. So at this point, just sort of trust. We have mass of x in every term. So mx, 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 and mx go away. We now bring in our VA and our VP. So this is 1/2 L squared over mx squared Ra squared minus g mass of sun over Ra equals 1/2 times L squared over mx squared Rp squared minus g mass of sun over Rp squared. Oh, Rp, oops, typo, sure, typo. So if I get these terms together and those terms together, so I have 1/2, well, I have L squared over mx squared times 1 over Ra squared minus 1 over Rp squared. Don't forget the 2, is equal to, on this side, I'll have g mass of sun times 1 over Ra minus 1 over Rp. Ra, this distance right here, well, this distance is the focal length, or the distance from the center of the ellipse to the focal point. This distance right here is A. And so R sub A is equal to just a plus f. R sub p, the closest point is, well, that distance there is a minus f, so the difference between that and that, a minus f. So working this out, this becomes 1 over a plus f minus 1 over a minus f, which is a minus f minus a plus f over a plus f, a minus f, which is, well, the negative f minus f. The a's cancel out, and so we're left with negative 2f over a squared minus f squared. Over here, and yeah, I'll squeeze it in over here. When has that ever gone badly? So we have 1 over a minus f squared minus 1 over a plus f, backwards, plus and minus squared. So this is a minus f squared minus a plus f squared over a plus f squared, a minus f squared. And up here, so we have a squared minus 2af plus f squared minus a squared plus 2af plus f squared over a squared minus f squared squared. Up on top, we have a, when you distribute the minus sign here, the a squareds cancel out, the f squareds cancel out, and we're left with negative 4af over a squared minus f squared squared. If you recall back to the ellipse, I know that f squared plus b squared is equal to a squared. Therefore, a squared minus f squared is equal to b squared. So this just becomes negative 4af over b squared squared, or b to the fourth, and this becomes negative 2f over b squared. So my equation here is now simplified down to L squared over 2 mass of the planet squared times negative 4af over b to the fourth equals g times mass of the sun, negative 2f over b squared. We can get rid of some things. We got a b squared there and a b, to get rid of 2 of those. The negative signs can go away. I have that 2 and that goes in twice, and then those 2 cancel out. This f and that f cancel out. And so now I'm down to L squared over mx squared times a over b squared is equal to g m sub s. So we now have that b squared over a is equal to L squared over g mass of the sun mass of x squared. And if we come back over here, that's one of the things that we were trying to show. Boom. That part done. Now we have to do the next part. We need to show that E is equal to L squared A over G ms mx squared. Well, I know that this part is just b squared over a, so this is b squared over little a times big A, whatever that big A is. So now we have to figure out what that big A is. That comes from R is equal to 1 over a cosine theta plus this other term out here, a over b squared. Because recognize this is when where we got it from. So this right here is, well, since b squared over a is that, this is a over b squared. And we do know a couple of points here. We know that when theta equals 0, r is equal to a minus f. A minus f is equal to 1 over a plus a over b squared. We ultimately are trying to solve for a here. So a is equal to, or a plus a over b squared is equal to 1 over a minus f. So a is 1 over a minus f minus a over b squared, which is b squared minus a times a minus f over b squared a minus f, which is b squared minus a squared minus plus af over b squared a minus f. Again, I know that b squared plus f squared equals a squared. So this would be b squared minus a squared is negative f squared. Flip those around or switch them sides. And so capital A is negative f squared plus af over b squared a minus f, which is, well, we can factor an f out of that. Factor out an f. I'll just factor out f. So I'm left with negative f plus a over b squared a minus f. Those minus f. Those will cancel out, and I'm left with f over b squared. So we need to see, is the eccentricity, again, we're trying to show that if the eccentricity is b over a times capital A, well, I now have something for that. So this becomes becomes b squared over a times f over b squared, which is just f over a, which is the definition of eccentricity. Done. So we have finished doing that Kepler's first law.